Hi everyone, this is Matt Teachout with Intro Stats, and today we're looking at an example from my book. This is section 4C, problem number 34. So we're in the two population proportion section, and we're looking at using randomized simulation to actually perform a two population proportion hypothesis test. All right, so let's read the problem. A study was done to see if there's a relationship between the age of a person, teen or adult, and using text messages to communicate. A random sample of 800 teens, population 1 found that 696 of them used text messages regularly to communicate. It's important to know that this really is sample data. That's not the population data. Population 1, they're just telling us, is the teens. And then a random sample of 2,252 adults. Adults were population 2. Found that 1,621 of them used text message regularly to communicate. Test the claim that the population percentages are equal for the two groups, implying that age is not related to using text messages. Okay, so again, this idea of related, if the groups were equal, then it wouldn't matter if you're a teen or adult, right? Your probability of using text messages would be about the same. That means it doesn't matter. So that would mean the being an adult or a teen is not related to texting. It basically they have about the same chance of texting. So that's kind of the idea behind it. It says use a randomized simulation in StatKey and a 10% significance level to test this claim. Okay. All right, so let's go back to StatKey. We're looking at difference in proportions now. So it's right there, test for difference in proportions. Okay, and just want to see, was this data already in there? They have lots of cool data sets actually in StatKey. Yeah, I don't see it there. Okay, so we're just going to type it in. So we're going to go edit data, and we're going to go in. Now, they did say they wanted me to use the teens as group 1, so 696 out of 800. So 696 out of 800. And for adults, it was 1621. 2252. 1621 out of 2252. There, okay. So there we just put in our put in our data. These are samples number of counts or number of successes out of the total sample size. And we're going to push OK. And there we go. So we can see on the here that our sample proportion for texting for teens was 80.87, about 87%. Sample proportion for adults was about 0.72, 72%. And the difference, subtracting them, is 0.15. So the question would be, is this 0.15 significant? Or is it just the result of sampling variability, random chance? Is this just sampling variability at work, or is this really indicating that the populations might be different? All right, so we got our null hypothesis that they're equal. We're going to generate 1,000 samples. Again, it's simulated samples under the premise that the null hypothesis is true. This is called a randomization test or randomized simulation. There we go. I'm going to click 1,000 a few times. All right. So we can kind of see this does look normal. By the way, this would have passed the 10 successes and 10 failures requirement. So we could have actually used a traditional z-score test statistic for this test, but the simulation does work well. They were saying we're testing that they're the same, right? So that would mean equal to. So the null hypothesis would be P1 equals P2 or pi1 equals pi2. And then the alternative would have to be not equal, right? The opposite of equal would be not equal. So we're going to go pi1 is not equal to pi2 or P1 is not equal to P2. And that would be a two-tailed test. So we're going to go two-tail here. Now they did say they wanted me to use a 10% significance level. So again, 10% broken up into two tails would be 5% in each tail. So I'm just going to put in 0.05, 5% in each tail, and the other one should adjust, yeah. So here's our 10% significance level broken up into two tails. We got 90 in the middle. Now, here is the tails. So the computer thinks that a sample difference, anything sample difference above 0.028 would be significant, and anything below negative 0.029 would be significant. So the question is, what was our original sample difference? Well, it's right here. By the way, don't get confused. These randomized samples are just the information on all of these simulated samples, and they actually change depending on which one I'm looking at. But the original sample is what we're worried about, what we're thinking about. The original sample difference was 0.15. Where does 0.15 land? Well, it's like way out in the tail, right? Even 6% would have been, 0.06 would have been significant. We're at 0.15, 15% difference, so very significantly different. This is, by the way, telling me that the sample proportion for teens that text, 0.87, is way higher than the 0.72 for the adults. It's in the tail, so it is significant. So the sample data does significantly disagree with the null hypothesis. All right, what about the p-value? Well, the p-value would be the probability that this original sample data happened. So in this case, we're looking at the sample difference right here. So since these are simulations of the sample difference, you put the sample difference down here. So in this right box here, if it was negative, I'd put it in this left box, but we have a positive 0.15 difference, so I'm going to put it in this right box here. So 0.15, which was the actual original sample data difference. All right, looks like it's way off the charts, right? Looks like we got a 0 p-value and a 0 p-value in each, a 0 probability in this tail and a 0 probability in this tail. Remember, in a two-tailed test, you have to add the tails. Well, that's not going to be too hard in this case. 0 plus 0 is going to give us a 0 p-value. So our p-value is 0. So if the null hypothesis was true, there's about a 0 probability of getting the sample data or more extreme because of sampling variability. Okay, so that would mean we what? Rejected the null hypothesis, but the null hypothesis was our claim. So that means we must be rejecting the claim. So this data really is kind of telling us that that claim that the percentage of teens that text and the percentage of adults that text being the same or equal is probably not true. So we're going to say there is significant evidence to reject the claim that the population proportion or population percentage of teens that text and the population percentage of adults that text are the same. So we're rejecting that claim. Our data actually kind of indicates that they're very different. And that that teens actually, the percentage of teens is actually quite a bit higher than for adults. Okay, all right. So this again is Matt Teachout and Intro Stats, and we were doing number 34 on section 4C.